Hi, I'm a vegan. I want to talk about fusion-fission hybrid reactors. Fusion and fission are capable of producing a lot of energy, but each have their own drawbacks. One of the problems with fission is the nuclear waste that is produced. Another problem with fission is the required enrichment process. For example, uranium-238 cannot be used in a fission process, so it must be enriched to get uranium-235, which can be used in a fission process. Some of the problems associated with fusion is that the process not hit break even, which means that more energy is required to start the process than we get out of it. Another problem is that the tritium fuel is very rare. Fusion conditions are very harsh, so they're not very conducive to sustainability, meaning that we can't run a fusion reaction for long. A solution to these problems is a fusion-fission hybrid, in which the fusion reaction is used as a neutron producer for the fission reaction. Ari is going to talk about the design aspects of such a thing.
Currently, we have a working fission reactor, and the two leading fusion reactors are the tokamak fusion reactor and the inertial confinement fusion reactor. The ICF uses lasers to send in pulses and compress a fuel using a DT pellet. And when it compresses, it sends in a shock wave and starts a fusion reaction in the center, which radiates out and ignites all of the fuel, or most of it. And once this happens, we can take that, the neutron source is coming off and the fuel and the heat from that, and surround it with a fissionable material, and this will start a fission reaction. The fission will be self-sustaining. We also have the tokamak reactor, and we can incorporate a fission reaction into this. Toroidal field magnets and essentials and other magnets surrounding it can control a plasma reaction in the center here, and once this happens, we can take the excess neutrons from that and start a fission reaction by putting a fissionable material surrounding it, like the ICF. Both of these are theoretical, and Brandon will talk about some of the implications of both of these reactors.
As Ari previously mentioned, the design of the ICF reactor and the tokamak reactor, both will be using the deuterium-tritium fuel, as according to this equation. If you fuse deuterium and tritium, the output is about 17 million electron volts of energy and helium and 1 neutron. This neutron goes on to drive the fission reactor. In normal traditional fission reactors, you need uranium-235 to be fissioned, which is really rare. It occurs really rarely in nature. The most common uranium isotope is 238, which cannot directly be used in a fission reactor, but if we implement a fusion-fission hybrid, we can put this very, very common 238 isotope into the reactor. If we couple that with the high neutron flux from the fusion reactor, we can use this 238, have it absorb absorb 1 neutron after 2 beta decays, which is the equations I wrote up here. We will eventually get plutonium-239, which actually can directly be used in a fission reactor, and that will produce some energy. Since our fusion-fission reactor can convert previously unfissionable material into fissionable material, the power output of this hybrid reactor would be much higher than that of a traditional fission reactor alone. Also, the high neutron output of the reactor, of the fusion reactor, can be used with lithium-6 to produce helium and tritium, which tritium is the valuable output here. Tritium will go on to driving the fusion reactor.
So some of the challenges that come with making a hybrid fusion-fission reactor include the proximity of the hot plasma to its surroundings. So you need a lot of superconductive material, such as supercooled supermagnets, to keep the material away from the walls, which at the temperatures of several million or trillion degrees would melt or ionize them. The other issue is keeping the radioactive waste away from the plasma, because there's a lot of unknowns about what happens when those two get close together. And there's a whole issue with developing a material that can withstand separating plasma at such a high temperature and the fuel that we need to fission for the fission part of the reactor. And that obviously leads to a lot of safety issues. Also, as Avik briefly said, there's a lot of energy required to go into a fusion before you get any energy out. So there's a higher point of energy required to break even as opposed to regular fission reactors.